Welcome to Matrices Part 2. This is the second part and the last part. Just like in the first part, I'm going to use an old video, so bear with me when it comes to the bad audio quality.
So let's cool our tongues a bit, or rather our heads a bit, by taking a look at something interesting we can do with matrices, and that is determinant of a 2 by 2 matrix. So given a matrix M, then its determinant, denoted by M with those two lines, is given by A multiplied by D minus B multiplied by C. So here's an example. Find the determinant of the following. The first one is matrix A. So let's take a look at the solution. So given this matrix, we can get the determinant by 2 multiplied by 3 minus 4 multiplied by 1. And simplifying this, we get 6 minus 4, which gives us 2. Let's take a look at another example. So find the determinant of the following, and that is B. So here's the solution. The determinant of matrix B is negative 1 multiplied by 6 minus negative 2 multiplied by 3. Simplifying this, we get negative 6 minus negative 6, and this is equal to 0. Let's take a look at the last example. So it's C, matrix C. Find the determinant of matrix C. So C is equal to 1 0 and 0 1. So its determinant is going to be equal to 1 multiplied by 1 minus 0 multiplied by 0. Simplifying this, we get 1 minus 0, which is just equal to 1. Let's take a look at a few more properties, maybe 2 or 3, that we're supposed to know when working with matrices. They're usually helpful. So the first is called identity matrix. So it is denoted by this symbol I, and this is a matrix such that when you multiply it with M, it gives you M. It's just like the number 1 when you are talking about numerals. So 1 by 5 is 5, 1 by 7 is 7. So an identity matrix is a matrix which, if multiplied by any other number, you get that number. So M by I, you get M. So another interesting property, or another thing we need to know about matrices, is the concept or the knowledge of leading diagonal. So given a matrix like this one or this one, then this is called a leading diagonal. So is this. Given an M by M matrix, and if its leading diagonal is equal to 1, that is, all the elements of its leading diagonal are 1s and the rest are 0s, then that matrix is called an identity matrix. Let's say we have this matrix. We can see that the leading diagonal is 1s and the rest are 0s. Therefore, this is an identity matrix. Given this one, we can also see that the leading diagonal contains only 1s and the rest are 0s. So this is an identity matrix. So another property is a matrix with 0 determinant is called a singular matrix. So any matrix that has 0 determinant is called a singular matrix. Like this one, the determinant is 0. Like so, 1 multiplied by 0 minus 1 multiplied by 0, we get 0. Now that we are done with finding the determinant of a matrix, we can take a look at the last thing we can do with matrices, and that is finding the inverse of a 2 by 2 matrix. So given a matrix M, then its inverse, denoted as M with that superscript, is a matrix such that if multiplied by M, like so or so, gives us an identity matrix. Remember, an identity matrix is a matrix with a leading diagonal that has 1s and the rest of the elements are 0s. So an inverse of a matrix is like a multiplicative inverse of a number, or rather a reciprocal of a number. So for example, if we say 4, its reciprocal, it's 1 over 4. So if 4 is multiplied by 1 over 4, it gives us 1. So how do we get the inverse of a 2 by 2 matrix? So given this matrix, we do the following steps in order to get its inverse. So first, find its determinant, which is always equal to AD minus BC. Secondly, exchange A and D like so. Thirdly, change signs of B and C. So if it was negative, it becomes positive. If it is positive, it becomes negative. Fourthly, multiply by reciprocal of determinant. So multiply the matrix that you have found on step 3 with the inverse, or rather the reciprocal of the determinant, and we will end up with something like this: 1 over determinant of M multiplied by that matrix. So this is its inverse. Let's do an example. So find A inverse given this matrix A. So here is the solution. So our A is this. So first thing, we find the determinant. So determinant of A is equal to 4 by negative 2 minus negative 1 multiplied by 3, which gives us negative 8 minus open bracket negative 3 close bracket, which if further simplified gives us negative 8 plus 3, and we get negative 5 as our determinant. The second step is to do the exchange and the inversing, and we get this, that is negative 2 takes the place of 4 and 4 takes the place of negative 2, and then we change the signs for negative 1 and 3, and we end up with this. After getting done with this, we then write our inverse as 1 over determinant, which is negative 5, multiplied by the matrix we got above. And if we multiply the constant outside, the constant being 1 over negative 5, we get this. So this is our inverse. So here is the solution. So we first find the determinant of B, which is 4 by 2 minus 4 by 2, which gives us 8 minus 8 and 0. So a matrix with 0 determinant is a singular matrix, and it has no inverse. If you try to get the inverse of a matrix that has 0 determinant, you're going to find out that you end up with something undeterminable. So the last question is find C inverse given this matrix. So here is the solution. So we first find the determinant of C, which is equal to negative 1 by 5 minus 2 by negative 4. Simplifying this, we get negative 5 minus negative 8, and this is going to be equal to negative 5 plus 8, and finally it's going to be equal to 3, and this is our determinant. So the next thing is, of course, to do the exchange and the reversing of signs. So we're going to end up with this, that is 5 and negative 1 are going to exchange places, and 2 and negative 4 are going to have their signs reversed. Therefore our inverse is 1 over determinant multiplying with the matrix we got, and further simplifying this, we end up with this. So that's all about inverses.